And we're back again. It's a new day. Hopefully everybody's healthy, happy. Maybe the sun's shining. It hasn't been shining around here. It did a little bit yesterday, but basically been wet all week. So we're going to continue on here with our physical geography online classes. Today we're doing chapter 16, Fluvial Processes. Again, it comes out of the Pearson book, the McKnight's Physical Geography of Landscape Appreciation, as well as the slide backgrounds and stuff. All right, so let's keep rolling. Today, streams and stream systems, stream channel structure relationships, the shaping and reshaping of valleys, floodplains, and so on and so forth. Again, I'm going to try to do all of this in one tutorial, not two, so I'm hopefully going to get it done. One thing is it may be a little long, so you'll find out. If you see this, then I got it done in one. If you don't see it, it's because I had to redo it and had to do it in two parts. So what is a stream? A stream is any channeled flow of water. Remember that, channeled flow of water. Fluvial processes are those that involve running water. Okay, so fluvial process can be anything that involves running water. Overland flow, unlike stream, overland flow is the downslope movement of unchanneled water, like off a cliff or something. Okay, you got something coming down a mountain, you got the stream in the mountain, that's your channeled water, and then sometimes you just get this overland flow to where the water's just rolling off the side of a hill or a cliff or something like that. All right, or outside the channel, for instance, flooding. Okay, that's unchanneled water. Stream flow is the channeled movement of water. So stream flow, pretty much the same things. Stream flow, though, occurs in valleys. Okay, and the valley's a low spot, right? So what are valleys and interflows? Oh, valley is a portion of terrain in which a drainage system is established, usually the low area. Water runs downhill, right? And also takes the path of least resistance. So once it gets to the bottom, that's when it starts incising and creating a channel. An interfluve is the highland above the valley walls that separates the adjacent valleys. Every stream, no matter how big, little bitty stream, big river stream, they all have interfluves. They're all separated. So we have high spots as well here in Oklahoma with our interfluves. For instance, the Cimarron is separated from the Arkansas, which is separated from the Red River, which is separated from the Canadian and the North Canadian. That means there's high spots in between each one of those. They have their own little stream channel down through the valleys, and then they're separated by high ground. Okay? Drainage basins, watersheds, basically the same thing. We're going to get into these. A lot of this has to do with size. So whenever you're talking interfluve, you're talking anything that is high on each side. So for instance, we have two very large interfluves here in the United States. Now, I'd love to ask you in class, but I can't because you're on here and I'm on here, so this is just the way it works. But think about this. Colorado Rockies, that's an interfluve. Everything that rolls off the west goes into the Pacific Ocean. Everything that rolls off the east goes out and down the Mississippi River Basin and into the Gulf. The Appalachians, everything on the east side of it goes to the Atlantic. Everything on the west side, all the water flow goes down again through the Mississippi River Basin and into the Gulf of Mexico. So those are also known as continental divides. So you have continental divides as interfluves. So even though they're mountain ranges, they're interfluves, okay? So drainage basins work the same way. Every stream has a little drainage basin, okay? And so these little drainage basins are for each little stream. Even if it's only a little stream that runs 10 feet, it's got an interfluve and a drainage basin, okay? But then we get ramped up in size. So one river runs into another river, so on and so forth, and they get bigger and bigger. Well, this Cimarron has its own drainage basin, okay? The Canadian, the North Canadian, the Arkansas, the Red River, okay? They all have their own drainage basins. And then if you combine those all together between Rockies and Appalachians, now you have a watershed, okay? Same thing. It's basically a drainage basin, just on a grander scale, okay? Areas that drain to the valley. So all these drainage basins, all the water goes into that particular watershed. And again, your drainage divide, interfluve, continental divide, depends on the grand scale of it all, okay? Stream orders. Now, most people use rivers and streams and gullies and rills and this and that and the other, but that's not really the way it works, okay? So we, in science, for the most part, use stream orders. We don't use the word river. We use stream order, and we number them, okay? So smaller streams join larger ones. Here we go. Let's get out my handy dandy little pen here. So as you can see, we got this one here and this one. So two ones make a two, right? There we go, two twos. And then two twos, right, make a three, okay? This relationship is called stream orders. So first order versus second and third order, and then the smaller numbers in a stream order are more frequent. So you got to have a lot more ones, right there, a lot more ones before you can have twos or threes or fours, right? Now, large numbers mean longer in length in watershed order, and that is because it goes all the way to, for the example, this 3 that's right here, it goes from here, and when you measure, you're measuring all the way up, not just to where it connects, but all the way up to its headwaters. That's where the whole thing starts, okay? It starts at the headwaters, right? Now, got to be careful though. So some people think, oh, the bigger the order, the bigger the river, right? Or the bigger the stream. Not necessarily. We have what we call exotic streams. And believe it or not, exotic streams have no tributaries. Therefore, they are on the order of 1, even though they're a very large stream. For instance, the Nile. No tributaries. It's a stream order of 1, but it's a big river. So be very careful when you're looking at stream orders. Don't just think, oh, it's stream order of 5, so it's got to be a big river, a big stream. No, not necessarily. Okay, it can be lots of little ones put together, and it just happens to be a 5, but it ain't no bigger than your city street. Okay, no wider than that anyway. And at the same time, it can be an order of 1, no tributaries, and that bad boy can be as wide as whatever, okay, as the Mississippi, okay? So stream orders. All right, so we have different types of erosion by overland flow, okay? So first of all, we have splash. Raindrop hits dirt, displaces dirt. Simple, easy. Sheet erosion. That's where that water comes flowing across, kind of associated with floods or coming off a cliff, something like that. That's sheet erosion. Large amount of water, okay? Rill erosion. What is a rill? A rill is basically an ephemeral stream. It's temporary, all right? You ever been across a road cut and you see where the water was trickling down, it cuts the little lines? Those are rills, okay? Those rills. They're there and then they get washed away and they have new ones, and so they're constantly changing. Gully erosion. Gullies are a little more stabilized, right? And so, but they're usually dry, right? Don't have any water unless it's a thunder boomer, right? So you got rills on the small order, and then you got gullies, and then gullies can lead to streams, and streams lead to bigger stream orders, and so on and so forth, okay? Erosion by stream flow. Once channeled, the erosion is greatly enhanced. So once you get that in there, it starts incising, it starts moving things around. Erosion is increased by the debris the stream flow picks up. Now, this all depends on how much water is flowing and when, right? For instance, you get here in Oklahoma, springtime, the Cimarron River, it's full of water. You got trees and everything rushing down it, right? Summertime, though, when it's really, really dry outside, it's more of a braided river. There's barely any water in it at all. So, again, it depends on the time of year. It depends on where you're at. Arkansas, we'll talk about it here in a minute, but Arkansas, when all the snow's melting, man, that bad boy is running. But then you get later in summer, oh, it's still running, just not as much. All right, chemical weathering and corrosion. So along with everything else, when water and rain is flushing everything into these rivers, you get nitrogen, carbon dioxide, everything that's in your atmosphere. You got to remember, if it's the atmosphere, the rain's going to wash it out. Okay, and all these things get eventually into the channel, and so you get chemical weathering and corrosion, right? All right, transportation. Now, you need to remember this figure here, okay? Because if you can figure out this figure, it helps you later on when we do aeolian or wind-blown processes, okay? So stream load. What is stream load? Sediment collected at the bottom of the stream. It involves the bed load, okay? That's the bed load right there. That's the load that gets bounced around, right? Through salitation and traction. Depends on how big the cobbles and stuff are, right? So if it's a bigger rock and the water's not flowing too fast, it's just going to kind of scoot it along. Water flow picks up. It can take that same rock and start bouncing it down, right? Okay, that's your bed load. Dissolved loads. That's your clay. Remember, I told you got to mix clay up. You got to decant it. So clay sticks to the other rocks. So you get all that cycling around, and the clay will dissolve into the water. That's your dissolved load. And then suspended load, that's usually your silts and maybe some of your finer sands, okay? And they float. They don't dissolve, they just float. Now, how does this all work? Well, as the stream is flowing fast, all this stuff's bouncing around, moving around, the whole works, and then the stream starts to slow down. And the first thing that falls out is the rocks. And then the next biggest size is the sand. And then the silt. And if it slows down to just almost a halt, even the clay will eventually settle out, okay? And that's why you look at those striations we talked about when we looked at our soils and stuff, those striations, those horizontal layers, right, that strata, that's why you get that layering. It's because when it was developed, it was the water volume slowing to slowing, and everything started falling out because different things weigh more. Heaviest stuff falls out first, lighter stuff last. Right, stream competence, particle size a stream can transport. Otherwise, can it do a big boulder or just sand? Well, you go up the Colorado Rockies, the Arkansas, full of big rocks that have fallen off the mountains and stuff and been washed down and everything else. All right, big rocks. It's steep. It's got gradient and you've got water volume, okay? Therefore, the competence load is larger. Now, you get down to Cimarron by Stillwater and the competence is much smaller. It's sand. Could you imagine trying how much water it would take to push one of those big Arkansas River boulders down through there? It'd take a lot, okay? So anyway, competence, the size, and that depends on where you're at, the slope, and the water volume, okay? Stream capacity, amount of the solid material a stream can transport. A stream can only transport so much and it becomes thick mud, right? So you gotta have a decent flow to keep that stuff moving, all right? If it becomes too much like a mud flow, then, well, that's a debris flow or a mud flow. That's not stream anymore. That's something else, okay? The role of floods, amount of water in a stream discharge, okay? So a stream can only handle so much water. Once it goes outside the banks, it's a flood, all right? Most excavating of valleys is accomplished during flooding, and that's because when a flood gets outside its banks, it starts picking up everything and moving it. Trees, and it all depends, again, water volume and slope, or gradient as we call it. It picks it up and it's pushing it, okay? Stream gauges used to measure flow characteristics. So again, we're going to get into this. The N+1, whenever I review for the lab test, we will go over that during the lab test, okay? You don't need to know that right now. Flood occurrence in 100-year floods. Well, we've got more flooding all the time, right? Global warming, sea level rise, blah, blah, blah. We're getting there. The thing is, you got to look and decide, well, how far back does it go? You know, our records. Do we really know what a 100-year flood is? And flood insurance can only be bought through the government. They own it hands down. Okay, you can't buy it through anybody else, and it's expensive. All right. So we'll draw here a little bit. So we have terraces on each side of our valley here, right? Boom. Here's my stream right there, okay? Then I got my terraces up here, All right, there's my terraces. All right, so as this water is incising, this is our modern day terrace right here, okay? This here is our modern day terrace, all right? And I know I can't draw, but hey, work with me, all right? And as the water flow comes up, then it starts cutting into these other terraces and others. Basically, the highest terraces are what we'd consider, for the most part, 100-year terraces. That means you've got a lot of water flow. But that's as the water goes down. So the rivers were originally up here. And then as the water went down, water volume and what have you went down, they started incising and incising and incising. So hopefully you understand that. All right, stream channel patterns, 4 categories. Oh, you do need to know these for the test. Straight channels, short and indicative of strong geologic structure control, otherwise usually along a fault line. There we go. Sinuous channels, irregular and gentle curvature that is sinuous in appearance. Again, depends on what type of soils you have or rock structure, geologic rock structure underneath. Now, there's a difference between sinuous and meandering. Meandering is all over the place, okay? A sinuous, here we go, sinuous is just nice, smooth curves just like that. Okay, not straight, not meandering. However, a meandering river, let me erase that. A meandering river is one that comes and does all this crazy stuff like so, okay? It's just all over, all right? So there we go. So sinuous channel, irregular and gentle curvature that is sinuous in appearance. Meandering channels, highly variable curvatures. And what you see in our figure over here on the right-hand side, that is a meandering stream. All right, and we've got a couple of things that we can look at here real quick. here is what we call an oxbow lake. So what has happened is this river was coming along here, okay, and it was turning into here, but over time it eroded and eroded and eroded and eroded away, okay, at that embankment there until it finally cut through, and when it cut through, the new channel comes down through here, okay, like so. So that's called an oxbow lake. When it dries out, it's called an oxbow scar, okay, and we'll look at that more in depth here in a little bit. Braided streams, multiple interwoven channels separate by loose bars or islands. You find these mostly in mountainous regions, I would say. Cimarron, they classify it sometimes as braided. It depends. If the water level's down and the sandbars are there, yes, braided. Springtime, the water's level up, it's meandering. It's going back and forth between the embankments, okay? So it depends on what time of year and depends on your definition, okay? Braided streams, usually big rocks, big sandbars and what have you that separate everything. And these crisscross for the most part, okay? So your stream channels kind of crisscross, go different directions, and they've got sandbars dotting them and kind of, you know, directing where they go. So braided streams, multiple interwoven channels separated by loose bars or islands. So stream development, structural relationships. Stream development affected by many factors. One's topologic, one is geographic. Okay, the most important factor is the geologic and topographic structures. Consequent versus slope and subsequent versus fault. So consequent streams means that the slope is dictating what's going on. Subsequent streams means a fault line is dictating what's going on. All right, so I've got some compression here, I've got some folding, looks like some faulting here. So we've got compression here, maybe some faulting here because we've got some uplift. So this is the geologic, and then the topographic has to do with slope and angles. So here's my slope, right? This is my topographic. It's coming off this slope. So again, subsequent versus consequent. Antecedents, those that existed before new uplift. This is an antecedent, existed before, and it incised. And then superimposed streams are incised streams, okay? So here we go. This has been incised, it's antecedent, superimposed. This could also be antecedent because it was already here, but now we have uplift, okay? So there's some different things going on. So just know that there's a bunch of different names. Now, do you need to keep track of this? Absolutely. Consequent slope, subsequent fault line, antecedent, superimposed. So what we have is we have some geologic stuff going on here that adds to the topography. And if the water's coming off this slope long enough, it might find a new valley maybe here, right? So we have different things going on that can happen, okay? Stream drainage patterns, dendritic pattern like tree-like pattern with a random merging of streams. That's what we mainly see in Oklahoma, dendritic, okay? All of them kind of coming in. Trellis pattern, forming areas of hard and soft bedrock. Geologic, right? Hard and soft bedrock in close contact, shape modified by the structure of the bedrock. So here we go, right? We got our thing here, and look at these. All of them coming in basically at a 90 degrees, okay? So that's that soft bedrock right there. So that's our trellis pattern. Radial pattern. Streams descending at concentric uplift associated with volcanoes. Might need to remember that, okay? Might be important. Basically, though, radial patterns have two drainage patterns. One that drains to the inside of the crater, and then one that drains off the outside of the crater. So that's how you know your radial. It's basically got two drainage patterns. Where centripetal pattern, okay, it's coming off, kind of like LA, coming off of the mountains around LA and what have you. Okay, everything drains out to the Pacific and down through the LA basin and what have you. Okay, boom. Okay, it's all draining off the high area into the Gulf or the basin. Okay, centripetal. All right, and this is what I like here. Here's my in-class object association for the day. So hopefully you're watching these and learning these because these will be on a quiz. And this will be probably the last time I tell you what's going to be on a quiz. I'll just put up in-class object association. Hopefully you get it right. Oh, my picture there is blocking one of my photos. Did not realize that, but hey, it's okay. So this is me and my kids on the Arkansas River up in Colorado. This is when they were quite young. And just to give you an association, these are class 3, class 4 rapids. They're known as the 7s. In the day we ran it, they were known as the 4s and 5s. 2 people died on this river the day before we went rafting, and 2 people drowned the day after. In fact, our guide did not want to take us. He was like, no, your son's too young, your daughter and him are too lightweight. They had to get another girl from the office to go. He was not a happy camper. I will tell you, it was one of the strongest workouts I have ever had in my life. I was exhausted afterwards. It was a blast. And after we were all was said and done, he got off, walked up to me and said, Mr. Cox, I will take you on any river, anytime. He goes, I've never seen a family like yours. So, just goes to show you, Cox has got some strength, baby. All right, so let's keep rolling. All right, valley deepening, down cutting, hydraulic power of the moving water to lower the stream bed. Right, so anyway, base level. What is base level? Base level, the lower limit to the amount of down cutting that can occur. Ultimate base level is sea level, and that is because here's my stream, right, coming down the hill, and here's my ocean, right? I'm trying to do my ocean here. Again, I cannot draw, but hey, work with me. All right, eventually, if you cut down far enough, you get to the ocean. Well, if you get to the ocean, what's going to happen? The ocean's going to start running into that stream, right? It's going to backflow. So the stream can't push because guess what? The ocean has more water, it has more volume, has more everything, more hydraulic pressure. It's going to stop the river and start pushing it back upwards, okay? So anyway, it's going to backflow. Nick points, channel irregularities such as rapids and waterfalls. Let's talk about waterfalls. Rapids, yeah, there's nick points because they get these things going, these little things going. But let's talk about nick points here as far as waterfalls go. All right, so first of all, it's covered me up here a little bit, but that's okay. You got the water coming off the waterfall, it's hitting the bottom, and it's going to erode this out. Remember what we said, differential weathering. We talked about that before, right? So we got differential weathering going on here, which means the softer stuff gets eroded away. And I've got this more resistant strata. I've got this cap rock up here, less resistant strata under, so it's going to keep eating it off, eating it out there, right? Destroying that differential weathering until this becomes too heavy. And then once this becomes too heavy, boom, it falls off, okay? So what happens? Boom, it falls off, which means you back that stream up a little bit. And then it's going to erode some more, and boom, we're going to back it up some more, okay? So it's nonstop. And then once you get to where the headwaters are, it's going to incise. The process starts all over until you get back to base level or sea level, and then it can't go no deeper. It can't go no further, and the ocean takes it over, right? So this is known as Nick Point migration. And again, Niagara Falls, largest one, it's moved like 300 feet in the years that they've been measuring it. So it started out 300 feet further forward than what it was, but it's eroded, blocks have fallen off, eroded, blocks have fallen off, so it's migrating, okay? Valley widening. Well, I kind of showed you this already with the terraces and everything, right? Boom, 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 boom. Here we go again. Right? Boom, 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 boom. Okay, valley widening. Right? So I've got my river. So what happens? The river's moving back and forth in here. It's moving. It's meandering. It's cutting out one stuff, eroding one stuff away, and depositing somewhere else. And it's just moving back and forth. That's widening. Widening slow when above base level. Okay? When above base level. Right? As gradient decreases, stream flow meanders and lateral erosion occurs. Okay? As it decreases, is the gradient, because as long as you got that flow going all straight downhill fast, it really isn't going to go nowhere. You slow it down and it starts kind of eroding. Not to mention, you got hard bedrock in the mountains. What do we got? Soil. Water takes the path of least resistance. Water moves outside of the fastest on the outside of the curves, the cut banks. So here we go. This is where it moves the fastest. You might want to remember that is the cut banks. Okay, the deepest, narrowest part right there. Okay. Here's my point bar. I'm covered up a little bit here, but I got a point bar here. So it erodes off the cut bank, deposits it on the point bar. All right. So here we go. Got my erosion here, and I got some deposition over here. Okay, erosion here and deposition over here, and that's just the way it works. That's where it deposits. Okay. Here's my Oxbow Lake. All right, because that meander cut that off. So at one time, this river kind of ran like this, right, and it finally eroded through and changed paths. Okay. Slowest water on the inside of the curves accumulates the alluvium or the point bar. So erodes in one spot, deposits in another. Valley lengthening, this comes back to our interfluve and kind of our Nick Point migration. This kind of better explains it. So here I go. This is my Nick Point up here, right? And so what happens, this breaks off and it breaks off and it breaks off. So your interfluve gets smaller, okay? as your valley gets longer. So you got to lose one for the other. Now, eventually what can happen is that interfluve can go completely away, and the two streams will join. The one coming off the one side, the one coming off the other. The interfluve is gone. They're going to join. Okay. All right. So headward erosion, fast-moving water from slope breaks between the interfluve and the valley will cause material to collapse. You get a lot of water under there. It's neck point migration. Results in decrease of interfluve area and increase in the valley area, lengthening, and causes a headward extension of the valley into the interfluve area. And if the interfluve goes away, the two streams can join. Which brings us to stream capture. Headward erosion causes one stream to be diverted to the base of another naturally. So here we go. We've got our two streams up here. Boom, 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 right there. Right? And what happened? This stream cut this one off. They were higher up, which is what this is called decapitation. It decapitated. It cut this one off. So these were higher up on the landscape. Okay, one cut into the interfluve, the other one just enough. So maybe this side was really high and this side had a really big drop off. Okay, so boom. So these two captured. So this is known as captor versus captured stream, and it's known as beheading. Okay, and the elbow of the capture. You need to remember this. This is the elbow of the capture. So when something has been captured, there's an elbow there. Now, what can happen? This can start eating away at this interfluve. So there's an interfluve right here, okay? It can eat away at this, and eventually these two streams could join back up, cutting this one off. Or maybe these two join up and cut this one off. So you got some high areas there with maybe a cliff or something on each side. You got some hydraulic work going. Delta formation. Slow flowed when it reaches an ocean. Again, because that ocean's pushing back on it. You got to have a lot of water flow. In the Mississippi and the Amazon have a lot of water flow. Okay, now, Amazon doesn't have a delta. Mississippi has a delta. We'll explain that here in a minute. So slow flow when a current reaches the ocean or lakes result in deposition or sediment. So it hits it, it slows it down, all that sediment's going to fall out. Okay, the debris builds up and forms a delta, and these deltas have what we call distributaries. Regular streams have tributaries. Deltas have distributaries because they're deltas. And because they're kind of more temporary. Streams have tributaries. Usually those are embedded, again, geologic, slope, all that good stuff. They move, but they're pretty much fixed. Distributaries, unless man has somehow built things up to keep them permanent, they move around a lot. And that's because they're like little fingers, right? So you got this stream coming out and it hits the water and it drops its load. So anyway, what happens? I get a big flood. I got a bunch of sediment coming down here, and all of a sudden it hits this. It hits this backflow area. Boom, stops, which means this is going to all fill up with sediment. And water takes the path of least resistance, so maybe this is a little more erodible here than what I just had, and it decides to take a new path. That's a distributary. They're a little more temporary than regular tributaries, okay? Because they're going to change. And again, unless man has, messed with them and put them more permanent with levees and things like that, okay? So again, here's my water. It's flowing. Oh, I got a storm that's coming in. Boom, stops it. That fills up. Oh, got to take a new path, okay? Distributaries. Deposition in valleys is known as aggradation. Remember these two words: degradation, destruction, aggradation, building up. Degradation, erosion, aggradation, deposition. Okay? All right, world's largest deltas and mouthless rivers. Okay, let's look at this real quick here. All of these red dots are the ones that do not have deltas. All the green dots are green triangles are the ones that do have deltas. Look at where they're located. How come the Amazon doesn't have a delta? It's a huge river. Okay, the Nile's got one, and it's a stream order of 1. Wait a minute, what's wrong with this? Well, it depends on where they're at and the ocean conveyor belt. The ocean conveyor belt, these gyres out here are constantly moving around, which means they keep the sediment from building up. The sediment keeps getting washed somewhere else. If you will look, all these triangles are on either the south or north sides of the continents or in protected areas. Okay, so my gyre is moving around here. My gyre is moving around here, right? Gyre. Remember, India is a whole different thing, but look at this. These are all protected because the gyre is down here, right? Okay, so depends on where they're at. Depends on how that ocean conveyor belt and those gyres and everything are working together. They keep that sediment constantly moved out, so a delta cannot form. Okay, Mississippi up in the Gulf, it's protected. The gyre is out here, right? So it can build a big delta. Nile, look at this. The Nile is completely protected. Builds a big delta. Okay. World's largest deltas, just so you know, this is them. You don't need to really take and memorize anything. This just goes to kind of show you the world's big deltas. Okay. Floodplains, low-lying near flat alluvial valley floor that is periodically inundated with floodwater. So what are floodplain landforms? Well, you're going to have bluffs on each side, okay, because of all the downcutting and everything else. Cut-off meander, that is also known as an oxbow lake right there, okay. Meander scar is when it fills in. Here's my meander scar. It's starting to fill in. Now, you can look at Google Earth and you can always tell where the meander scars are because the older trees are on the areas that have never had flooding or never been in the stream itself. And the newer, smaller stuff is in the meander scar. So you'll see your river, it's running, but then you'll see some little things, going on. You're like, what? It's a change in vegetation. The bigger, older stuff has been on more stable land or ground versus the stuff that's in the meander scar, okay? Natural levees, you just build up sediment on the sides. Those are some natural levees. Back swamps, that's when some streams can get blocked, and if they get blocked up, it starts kind of backing up, okay? Eventually, if it totally blocks off, you'll end up with maybe a saline lake or something like that. And then this one here, Yazoo Stream. Yazoo Stream is a temporary ephemeral type stream. Usually overflow from snowmelt, this, that, and the other. A lot of times it has to do with that geologic, like the sag ponds. Remember I said the geologic run along the fault line. Okay, you see these. These are temporary streams. They're kind of, and they usually run straight, but they're next to bigger rivers, and they're just temporary streams. Okay, overflow streams. Put it like. All right, modifying river to control floods. Humans live on floodplains. Yes, we do, because it's good fertile ground, flat land, abundant water, and productive soils. And we put in our man-made levees, dams, and overflow floodways created to avert disaster. Again, Hurricane Katrina, everything went wrong there, which is an example of the Mississippi River. And now if you come up into Oklahoma, we've got the largest inland port in the world there at the Port of Catoosa. So we've got the Arkansas system as well. Human-induced changes to deltas and floodplains. We want people to be able to live there. The thing is, if it's prone to flooding, you probably don't, right? So don't build things where it's probably going to get destroyed by a big flood. Lowering of sea level during ice ages or increasing of elevation from tectonic uplift increases gradient. So this is stream rejuvenation. We already kind of talked about this. You get down to that stream, it's about to die. It's almost ready to hit base level, right? Ultimate sea level. But then some tectonic action happens, it lifts up, and the whole process starts again. Again, look at this figure in the book. Okay, here it was almost to base level, ultimate base level, sea level, and then we ended up with some uplift, geologic uplift, and the whole process starts again. Gradient increase, restart, or rejuvenate vertical incisions of the streams. We've already talked about the terraces, okay? So here's the terrace here, see your high spots here, okay? And then your lower spots. And if you look at, if you had a blown up picture of this, you'd see there's a lot of different little terraces. And then these entrenched meanders, that's just incisement. So we've covered this pretty much. All right, theories of landform development. Here we go. Davis's geomorphic cycle. You need to know this. Continuous sequence of uplift, fluvial erosion, and denudation. Denudation, overall lowering of the landscape. Use stage. Look, it's flat. There's no real streams there, right? They haven't become permanent streams yet, right? They're just kind of temporary floating around. All right, and then so our use stage, streams become established and drainage pattern starts to develop. That's that drainage pattern. And then mature stage, streams approach equilibrium. Hey, I've got a stream here now, right? And I've got a drainage pattern, okay? Then we get to the old age, because guess what? This stream's been meandering, and it's basically gotten rid of all this higher land or that interfluve drainage basin stuff around it. It's eroded it all away. It's cut it all down. And once it cuts all down, well, guess what? We're almost back to, old age here, or youth. So our old age station, erosion reduces landscape to near base level again. And then the rejuvenation starts. What is the rejuvenation? New uplifts, and it restarts that cycle, kind of what we seen on the last slide. So I'm almost about to die. The river's about to die, be get back flooded by the ocean. And all of a sudden, some tectonic uplift happens, and the process starts all over again, okay? Equilibrium, I don't really get too much into this. Variations of influence across the movement and resistance of underlying rock. This has more to do with geologic and fault lines, folds, things like that. The slope forms to adjust the geomorphic process to achieve energy balance, shortcoming the areas that are tectonically stable. Prime theory used today. Again, I'm more worried about the soils and stuff and undercutting interfluves. But this is science, and you need science, right? All right, that's it for today. Hopefully this will all record in one show. Hopefully you enjoyed this tutorial. I will be posting a bunch of stuff fairly soon. I will see you on the other side.